everybody hear me up there? All right. So last time we solved some problems in anticipation of the midterm. I think let's do the same thing today. Midterm coming up, and we'll solve a few more problems from the homework. So when we solve these homework problems, by the way, every problem that we solve here obviously is not going to be on the exam. So it's a double win. First, you see good solutions, and secondly, you don't have to worry about those on the exam. How's that for a deal? The problem that we solved last time about the wall, when you go back and forth, you double the size of the trip every step. How many remember that? It converges to linear, interestingly. I just wanted to bring to your attention that that's a form of binary search. How many can see that? Abstractly, it's binary search. It's not the usual binary search. Binary search usually starts with a large range and divides it by half every time. That's how you search, like the phone book or any kind of assorted list, binary search. So log number of steps, and you converge smaller and smaller and smaller sections until you converge on a single thing that you're actually looking for. That thing with the wall is sort of the inverse of that. The binary search in reverse. You go for larger and larger and larger sections until you find what you're looking for. So we can call that exponential search. But it's the analog of binary search. Okay, just in the other direction. Instead of converging into smaller and smaller, you diverge into larger and larger. Either way, you find what you want within a logarithmic number of steps. Okay, so think about that as a variation of binary search. Let's call it exponential search. Any questions about that technique? You could use it in lots of different scenarios. For example, how is that used in hash tables? When a hash table, you put stuff in the hash table gets nearly full. And why does it get nearly full? First of all, why is it bad for a hash table to get nearly full? Why is that a red flag? Why should you avoid that? If a hash table is 80 or 90% full, something terrible could happen. What? It could take a long time to find something or insert something from the hash table, because you have to maybe do linear probing and just traditional hash tables, nothing fancy like hanging balance trees off the buckets, just normal hash tables. So the searches and the lookups and the insertions and the deletes could take arbitrarily long all of a sudden. It could take linear time each, roughly. So what do? Ideally, you want to create a hash table up front that's larger, maybe 2 or 3 or 5 times as large as what you expect the occupancy rate to be in the hash table. But you may not know what the size should be ahead of time, because things come in real time and you don't know how many things you need to store in the hash table at any given time, the maximum number. So you allocate some hash table that's reasonable size, like 100 or 1,000 or 10,000 elements, whatever is reasonable for that scenario. But then when it gets near full, what do? Let's say you underestimated the size of the hash table. You only allocated 10,000 elements, but now you realize you're going to have 50,000 elements halfway through the computation, or certainly exceed 10,000. Let's not put a number to it, but you need more space in the hash table. What do? Create a new hash table. How big should the new one be? Maybe double, maybe triple, but not 100 times the size, right? That's too much. And if that runs out of space, you double again and you double again. In other words, you're converging eventually on the true size by repeated doublings. And when you do all these doublings, what's the total time per element, amortized cost, after k doublings, after a bunch of doublings? Which as a function of the final size of the hash table. In other words, doubling a hash table, what do you have to do? Take all the elements and rehash them into the new table, and there could be a lot of them. So the doubling operation is expensive by itself. But per item, it's not expensive at all. Per item, how much are you paying when you double the size of the table? Asymptotically. Just to see if you have these concepts kind of straight in your head. Linear time, square root time, log time. How many say you're paying log time per item for doubling the table? How many say it's cheaper than that? Why is it cheaper? Yeah, you take all the items and put them in the other table. The table is only twice as big, so it takes twice as much as populating the original table that's half the size. But per item, you're only expending a constant amount of overhead. How many can see that? Only constant per item, yeah. And if you have to do it again, that's another constant. And again, that's another constant. What if you have to do it k times? You have to double it k times. You may have to pay k units per item, but the number of items is small at the beginning and grows and doubles and doubles. And eventually, what happens to your cost per item? Let me ask it a different way. You create a hash table twice the size. Then you create a new one for twice the size of that and repopulate it with the old stuff. Then you double it again and again. At the end, when you have a hash table of size n, what's the total amount of work you did up to that point? Just doubling and doubling the size of the hash table, rehashing all the old items into the new table and so on. The total amount of work you did as a function of n, the size of this final hash table, the biggest hash table you're going to end up with. Take a wild guess. You did n work roughly to populate the last hash table, the biggest one. The one previous to that, n over 2 work. The one previous to that, n over 4 work. The total amount of work you did is what then? It's 2n roughly. So you only took 2 units of work per item throughout this entire process, no matter how many times you doubled. I mean, there's no such thing as a free lunch, but something like that comes pretty close to being free. Anything that's only constant overhead for some useful, valuable operations, that's as cheap as it gets, right? Any questions about that? So that's another form of convergence, or another way of saying it, you're kind of doing an exponential search on the size of the hash table until you find the right size. And all that doesn't cost you much. It only costs you roughly twice the largest size, or less. Okay, so be on the lookout for converging sums, exponentials that you add them up and they converge, and then you don't have to pay as much as you would guess just from initial glance. Initial glance, you might think, oh, the total amount of work is n log n or even quadratic. No, it's linear. And per item, it's constant. Okay, any questions about that? All right. So let's solve some problems here. So there's a big one, number 54. We want to make a height balance tree persistent. In other words, we talked about data structures a couple months ago now. We talked about height balance structures like 2-3 trees, B trees, AVL trees, red-black trees, all kinds of height balance data structures whose height is only logarithmic in the width, or the number of items in the tree. It doesn't have to be a tree, whatever data structure it is. Let's go one better than that. Let's say you want to maintain a height balance structure, and I'm not saying what it is because it could be a lot of different things. This is going to be a general solution that covers a lot of ground. And you want to be able to do the following. You want it to be persistent. So when you modify the tree, again, I'm saying tree, but when you modify the data structure, you get a new data structure, and then you can search it or add to it. But you want to keep the version of the older one, the unmodified one, still around, so you can search it too. So you'll be able to search the entire past, all versions of the data structure as it gets modified by additions and deletions, adds and deletes. You'll be able to keep them around in some way so that those can be searched as well. You don't want to modify them, but you won't be able to search them. Okay. You can also do a more sophisticated version where you can actually modify the past. But let's say you want to keep the past around, all previous versions. Are there any applications you know of that actually keep around all previous versions of some data structure or document or file or? Yeah. So on the web, like when you use Google Docs and you keep modifying it, you can always go back to previous versions. It saves all of them. Right? How many have seen that or experienced that? Yeah, and it's a nice property to have, so that you don't lose some old version. If you can, by mistake mess up the version that you have now, no big deal. You can go back to last night's version or last week's version, or just out of curiosity, or just to have a historical record, an audit trail of all previous versions. It's a good property to have, to preserve the entire past. Of course, there's an easy way to do this. Copy the entire data structure, or file, or document, or whatever it is you're trying to preserve, and then modify the copy. Obviously, this will work. That's foolproof. But what's the catch? Every time you're going to change an A to a B in a Word document that's 10 megabytes long, you're going to create a whole new copy? Not so much. That's a big waste of space and resources and time to copy all these massive amounts of data. So you don't want to just copy the entire thing blindly and then modify the copy. Although that's an easy way to do it, it's just inefficient. So we want to do the following. We want to minimize the amount of extra space you use as you keep preserving these previous copies as the data structure gets modified. So, let's, for concreteness sake, let's assume it's a height balanced binary tree. Let's say it's a 2-3 tree or a red-black tree. Doesn't matter. Let's say it's a height balanced tree. You want to make a modification, either an insertion or a deletion. You get a new tree. You want to be able to still preserve the old tree in some form so that you can search any one of the previous trees, any one of the previous K versions. And K could be large. But you don't want to take space or even time proportional to K times the size of the tree. So let's say you modify the tree. Let's say the tree ends up being n items long. Fully populated data structure or tree, height balance, n items long. You don't want to create a copy of size n and another copy of size n and another copy of size n, because eventually after n operations you'll have n squared space. You'll be using n squared space. You'll be copying all n items n times for the addition of every single item or deletion of every single item. Don't want to do that. So how do you do it with some thriftiness in space? N times. And you still won't be able to search the past efficiently, by the way. So you're keeping copies of all the previous versions of the tree, and they too remain searchable in logarithmic time per search. So we're not giving that up either. So we want to do fast searches not just on the current tree, but on all the past trees, all previous versions of the tree as well. Logarithmic times per search. Okay. How many have worked on this problem? Only less than 10 out of 100. Okay, interesting. What if I just put it on the exam? I mean, will you work on it then? If you haven't worked on a problem there's a lot less value for you to see the solution. Just like, if you never, if you never ran in your life or exercised in your life, there's a lot less value for you watching the Olympics. It's still entertaining and it's still, not bad, but you can't fully appreciate what you're seeing, what you're looking at, if you have never tried to do any of those things, any sport whatsoever. Problem solving is not a spectator sport. You have to participate to get good at it. You have to try a lot. So I keep saying that. I don't want to beat on it too much, but if I don't bring it to your attention, and on occasion, like if you tell me you've seen this problem for 2.5 months now, but didn't even try working at it at all, knowing that these problems will be on the exam, I'm not sure what you're thinking. So, okay, let's leave it at that. Any suggestions how to get this done? Yeah.
Keep an array of size n of the tree, because any type balance tree is sort of determined by what the root node is.
Okay.
And then you can index that in constant time. I guess you only have the root. You would have to rebuild the tree to get exactly what the
Okay, so he's saying keep an array with pointers to all the roots of the previous trees, but then are you going to copy all these trees? In other words, each pointer in the array will point to a complete copy of the tree that's separate from all the other copies? And
yeah, it just points to what the value of the root node was, because if you rebalanced it, then the root changes.
yeah, but
Then
oh,
you can't get the tree itself.
okay, so you're on the right track. When you say reconstitute or regenerate the tree, this should happen very, very quickly, right? So you can search the previous trees quickly. So you don't want to have to waste a lot of time regenerating the tree, because if you only cared about space and not time, there's also a simple solution to that, and not an efficient solution, but a straightforward way to implement that. If you just cared about space usage, but not time usage. In other words, you will be able to search all the previous, versions of the tree, but time wasn't an issue. You just don't want to have to spend a lot of space storing a lot of stuff. What's the easy solution for that? And by the way, when I say data structure or tree, it could be a database, it could be an entire database. Yeah.
Store the operations.
Store all the operations you ever did, starting with the empty data structure. Store all the adds and deletes that you've ever done. And to find something in the past, go back to the beginning, reconstruct the tree up to that point that you're trying to find something, and then look there to see. But that's an awful lot of work to have to replay all the operations you did up to this point. There could be billions of operations on your data structure or database or whatever it is you're storing. So this will work. This is correct. It's just that's not very efficient at all. But it won't take much extra space. All you got to do is store, all the items that you ever deleted or added, and and in the right order, and then you'll be able to reconstruct the past. But the reconstruction operation will be a heck of an expensive operation. It won't be logarithmic time. We're going for logarithmic time. Other suggestions, but you're onto something. But you have to show how to get it to happen efficiently. Yeah.
So maybe we can copy a tree, but not after every operation, maybe after some certain number of operations.
Okay, so you're saying copy the tree, but not after every single operation. Maybe batch them up in groups of some larger number than just one, and then cache a copy away every so often. And that's another way to do it. But it will also take. There might be some issues if you're trying to search for something that's in between copies.
So you also save the operations, apart from operations.
Yeah, so it's kind of a hybrid. You save copies of the data structure, and you can save the operations themselves, and you only reconstruct. So this is sometimes called checkpointing.
Yeah.
You checkpoint something, and you go back to the checkpoint, and you only do the reconstruction from that last checkpoint forward, not the entire history. And that could work. Again, you'd have to figure out and argue how efficient it is and how often you checkpoint and what's the total amount of storage and so on. But if the checkpoint, there's a tension between these two parameters. If you checkpoint too often, like every single operation or every other operation, you'll have too much space for all these checkpoints. If you don't checkpoint often enough, you're going to have to spend a lot of time reconstructing because the last checkpoint will be way too much in the past, and you have to do a lot of reconstruction from that last check. So these two things are at odds with each other, which is okay. It's a trade-off, and you have to figure out exactly what the trade-off is and how efficient it is. What else? Yeah.
Can you store every changes to the structure of the actual tree, and then you won't need to recalculate everything, you just need to apply every change?
Yeah. So let's symbolically draw a tree. So here is the first tree. I'm going to draw it like this. Here's the root. So I'm drawing this binary tree as a bunch of subtrees. And now I want to make a change. Let's say I want to... Oh, nobody even said anything. How about that? All right, there's my tree. Don't let me do that because it makes me wonder if... Never mind. So I'm drawing this tree symbolically. These are big subtrees. These subtrees could be huge. Could be millions of nodes here, but I'm just showing you a general structure of a height-balanced tree. Let's say you make a change. You delete something or add something. Let's say you delete something here, way down in the tree. In a height-balanced tree, how long does it take to delete? How long does it take to add? Log time. Which means not too many things in a tree can change. And in fact, the things that do change in a tree when you add or delete, if it's height-balanced, are localized to a particular neighborhood or common place. Where is that place? Let's say you delete or add something right there where the red X is. All the changes that you told me there's log of them will be where? Symbolically in this. Will they all be below this item right here? Because if you add and all the changes are below the item and you keep adding and you add there again, and again and again, this will keep growing and it won't be balanced anymore. So they can't all be below that place. Right? So some of them could be right there, but others will be where? Upwards, yes. Specifically where? Towards the root. It'll be on the way from that item all the way up to the root. All the changes will be on the path from where the insertion or deletion occurred all the way up to the root. And that path is at most log because it's a height-balanced tree. How many believe that, understand that? Okay. When we talked about data structure, we even had animations of how these rebalancing operations work. They propagate up from where you did the addition or insertion or deletion. The rest of the tree in blue doesn't change. The only changes are along this path in red. So what we can do when we create a new data structure, instead of copying this whole data structure, I'm just going to copy this path, this blue path. So I'll make it, I'll keep it blue. All right, so I just copied this red path here. In fact, I should probably make it red, but either way, it's color coded. So here's the red path, color coded. And then the other subtrees in blue there didn't change. So what I'll do is I'll just create pointers. Instead of copying this subtree to here, because it didn't change, I can just point to it. And logically it's the same. How many can see that? Yeah. And from here, instead of copying this subtree here, I can just point to that. And from here I can just point to here. And from here I can just point to here. And from here I can just point to here. So all I need to do is copy this spine, this path to the root, and then all these big giant subtrees hanging off of that path, I can just put pointers to them because they're still there and they haven't changed. And that's the second item in the array that you mentioned. That's the second tree. So you have this big array up here, and in it you have a pointer to the first, a pointer to the second, and so on. How many are beginning to see what's going on here? Good. How much extra space does every new tree takes now in this scheme? Log n space. And all the trees there are there explicitly. The entire past is there represented explicitly, not in some coded way, not in some replay kind of reconstructing kind of way. They're there explicitly. So if you start descending into the second data structure there, you see exactly the original tree with the modification. And that's it. You don't have to do anything other than just search it in a binary search kind of a way where it's height balanced and it works. Yeah.
So we've seen one change. For a second change, would you just copy over the pointers that were copied for the first change into the second change? And then you would also outline that same path as well?
Yeah, so what you do now is you repeat, because the data structure in green here, this data structure, is nothing but a height balanced tree regardless of the first data structure. So to make a change in that, find out where the change is going to happen, copy the entire path here to the third copy, and then put pointers into the one from the second copy that didn't change. And you just keep going. And it'll be pretty convoluted. It'll be a lot of pointers pointing across in all sorts of weird ways, but each one is completely consistent. Each one, starting from the root, is a height balanced tree, no different than any of the other trees in terms of structure and height balancedness and searchability in logarithmic time. And so you're only saving the stuff that potentially changes, and that's log per operation. So if you have n items, so you have 1,000,000 items or 1,000,000,000 items, and you want to preserve the entire history of 1,000,000,000 changes to a tree with up to 1,000,000,000 items in it. That billion is n. How much total storage altogether does this cost you? To store all 1,000,000,000 trees of size n each. Each one slightly different because you keep making changes, additions and deletions. The total amount of space is asymptotically. N is 1,000,000,000, but it's n log n space. How many can see n log n space? Good. So it's not quadratic, and it's not something worse than log n. It's log n per new copy, and that's pretty good because a copy is 1,000,000,000 large, or whatever it is. It could be 1,000,000,000,000. So that's one way to answer this question. that was on the problem set. I'm sure there's other ways to answer it too. This is not the only way, the only thing you can do, but this is straightforward. It's playing around with pointers. It's taking advantage of the structure of height balanced trees. And it also tests your understanding of data structures, because we're just stepping a little bit away from normal data structure. And this is kind of an esoteric one, but it works out. Any questions, comments about this? Yeah.
Had a non-height balance, just like binary tree, and you did like the tree as big as the biggest like tree that ever was, and then the pointers to delete list the whole history of each node pointing. Would that also be like a balanced tree?
Yeah, so she's asking if this was not a height balanced tree, but a regular tree. And a regular tree could be very skewed, it could be very stringy, very long, very narrow. It could become almost like a linked list. It could be a non-height balanced tree can degenerate into a long list. Then this scheme, well, let's take two sub-questions. Will this scheme still be correct if you do this on a non-height balanced tree? Will this still work correctly? How many say yes? How many say no? Well, we have a split vote. Interesting. So I'm glad I split the answer into correctness, because my next question will be about efficiency. But if something is not correct, there's no point discussing how efficient it is, right? So let's first nail down correctness. So can you do this for any tree, not just height balanced tree? If yes, why? If not, what would stop you? What would stop this from being correct? Let's say the tree was not height balanced. Let's say it's way skewed, lopsided, deep here and shallow there, in all sorts of ways that are uneven. You can still modify that tree, first of all. You can add something to the tree, you can delete something from the tree, right? Nothing stops you from doing that, otherwise trees wouldn't be very useful. When you add or delete something from a tree, where are the changes? Well, they're somewhere, but they're not everywhere, right? In particular, they're also on a path to wherever it is you make the change, right? How many agree with that? No, not everything in a tree changes just because you add one element to a tree or delete one element to a tree. That's not a function of height balance. That's just how trees work. Changes are kind of localized. In height balanced trees, the changes can propagate up and down that path to the root because you're trying to preserve balance. But in a regular tree, you don't even have to do that. So the changes in the regular tree are even fewer than in a height balanced tree. How many can see that logic there? Yeah. Just add or delete nilly-willy. You don't have to worry about balance. Just chop it off right there and walk away. That's how you get rid of something in a tree. If you don't have to worry about balance. Same for addition. Just graft it right there and walk away. So this scheme will work whether the tree is balanced or not. How many can see that? Just copy what you changed and then put pointers into everything that's not changed, which is most of the rest of the tree. So this will work. It's correct. But how efficient is it? Will you still have n log n total space for n copies of the entire past? I mean, say you'll take potentially a lot more than n log n space. Yeah, a lot more. Because the entire tree could be one giant deep list going, with almost no branching off of it. And you're going to have to copy, the entire spine, which is the entire tree at that point, because it's one giant list. You're going to copy the list over and over and over again. And the space could be as bad as what for n tree of size n, or n additions and deletions to a tree? N squared. Could go quadratic on you. So back to the question there, yeah, it'll still work for regular trees or any arbitrary trees. It could explode quadratically, though it won't be bounded by n log n total space used. So So it's not really, it's probably not worthwhile doing that for arbitrary trees. Yeah, unless unless you really wanted to do that for whatever reasons, you better have some really good reasons to risk space exploding quadratically. I mean, that's a big risk. Okay, what else? Okay, so that's an exercise, playing with data structures and. So one less problem you have to worry about on the exam. How about that? My gift to you. All right, let's do the next one. Give an efficient algorithm. If you have n points in the plane, determine whether any 3 points are collinear. How many have worked on that? Oh, good, a lot of you. How many have a solution for that algorithm? Okay. How fast are we talking about? If you have n points, how fast is your algorithm? N squared log n. All right, that sounds about right. Anybody want to explain n squared log n? How would that work for finding a collinear triplet? 3 points that lie in the same line. If you have n points given to you. A lot of you said you had a solution, so let's hear one. Yeah.
So you could, for n squared, it's calculating the slope between every 2 points of the points in the plane, and then you could store the slope in the offset, the intercept, as a pair in a 2D matrix, and then I believe the log n is the search for the elements.
Mm-hmm.
So you can do slope or you can do polar angle.
Yeah. So he's basically saying, I'll paraphrase a little bit. He's saying, take every pair of points and look at the linear equation that they define, the line that they define. A pair of points define a line in the plane, right? Or even in higher dimensions for that matter. But in the plane, a pair of points define a line. So compute the equation for the line in terms of slope and y-intercept. That's one way to define a line. Give me the slope and tell me where it intersects the y-axis. That's the y-intercept, where it hits the y-axis. For case of vertical lines, what's the y-intercept? There is no y-intercept. But then you could just give me the x-intercept in that case. Either one is fine. But either way, you're uniquely determining a line by its slope and y-intercept. So if you have 3 collinear points, what can you tell me about the equations of the first 2 points and the equation of the second 2 points? The first pair and the second pair. First pair and the second pair. What can you tell me about the 2 equations? They're the same equation. How many can see that? Obviously. Because now a line is overdetermined by 3 points. They're all on it, rather than just 2 points that are just on it. Right? I mean, 2 points determine a line, but so can 3 points, so can 7 points determine a line if they all lie on the same line, obviously. Right? So, take all these lines created by all n choose 2 points, all n squared roughly points. Take all these lines and do what with them? Sort them. Sort them by what? By slope, and then within the same slope, sort them by y-intercept. And then what? Let's say they're all sorted by slope, and then second sort key is the y-intercept. What do you do next? Scan the list and do what? Look for equal objects, equal lines. Lines are the same as one another, same slope, same y-intercept. On a sorted list, they'll be neighbors, so you can just scan it linearly now. And the minute you find a couple of lines that are the same, What does that tell you about collinear triple? It's got to be there. In fact, this will find you not just triples, quadruples, quintuples, sextuples, septuples, octuples. That's why I think I run out of names. How you see they finds all those things? Yeah. So you're actually finding a lot more than what you're being asked to find, but you're also finding what you're being asked to find, and that's okay. If there's a collinear quintuple, within that there's a collinear triple, not necessarily the other way around. It's not an if and only if. All right, how long does all this take? Asymptotically is a function of n, the number of points. N squared log n. The time to sort was the bottleneck. Because you sorted n squared things. Yeah. Good question. He's asking, is sorting necessary? Sorting is sufficient. Sorting works. But very good question. He's asking, is it really necessary to sort them? Could you avoid sorting and thereby reduce the time, because sorting will no longer be the bottleneck? How many here can do it without sorting? How long will it take if you don't sort, do you think? Should be take hopefully n squared. Right? Let me answer it in the following way. You don't have to sort. You can find a collinear triple in n squared time. But it's not at all easy to do. In fact, it's so hard to do it that way that we're not going to describe it here. You can do it in quadratic time. You can find a collinear triple without sorting. Let me say something even more dramatic. Let me first ask you a question. Do you think you can do it faster than quadratic? Because all you're looking for is a triple. In fact, I'm not even looking for a triple. I'm looking for whether any triple exists. I'm not even necessarily asking you to give me a triple. Just tell me yes, no, one bit in reply. Is there a triple or isn't there a triple? I don't even care what it is if it's there. I just want to know that it is there. So I'm giving you n things. I'm asking you for one bit of a reply. And do you think it could be done in less than quadratic time? Because that's an awful long time for a single bit reply when the input size is n. I mean, even sorting takes only n log n, and I'm giving you n things, and you give me back n things. So that's a lot of input, output, and it's just n log n. Convex hulls, I give you n things, you give me n things up to n things back. Voronoi diagrams, I give you n points, you give me a big complicated Voronoi diagram back. That's n log n also. So it'd be hard to believe if I give you n things and you give me one bit in reply, you should have to spend quadratic time, worst case, necessarily. Right? I mean, you see the intuition behind that. It's just an intuition. This is not always true. There are problems for which there's n inputs, and one answer comes back as a single bit, and it's not just quadratic, it's exponential time is required, or even super exponential time is required. There's problems that have that property. In fact, there are problems that take arbitrarily long, even for the best possible existing algorithm that we don't even know what it is. There's lower bounds that are exponential or super exponential. But for this problem, collinear triple, how many, just intuitively, I'm not asking for algorithms or proofs or anything beyond just a guess. How many here think it can be done faster than quadratic, just the existence of a triple? Okay, how many say it can't? Quadratic is a lower bound. It's an open problem. Nobody knows, actually. If you can figure this out, that's not just an instant PhD in computer science. It'll also probably be a Turing Award because it's been open for decades, this problem. Whether a single triple can be found in less than quadratic time. It's amazing, right? Because the n squared log n algorithm, it wasn't that hard to come by, Form the lines, sort them, and then scan the list, and That's n log n. Quadratic is a tricky business, but there's quadratic algorithms too. They're just much more complicated than sorting and scanning. But whether it can be done in subquadratic time, it's open for decades, nobody knows. And it could be open for decades more to come. But let me just say that that subroutine of finding collinear triples is used in many other algorithms as a subroutine. And that's the bottleneck in many other algorithms. And if you can come up with a subquadratic algorithm for collinear triples, that will immediately improve the complexity of dozens and dozens of other major problems and algorithms in one fell swoop. So you'll be a hero on many fronts, not just. So it's a highly leveraged problem. Okay. Any questions, more questions about that? So, if this was on the exam, I would be happy with an n log n, with an n squared log n, and that would be fine. That's perfect, full credit. N squared log n. You can take a bow, you're correct. I wouldn't expect you to come up with quadratic. If you come up with quadratic, extra credit, of course. Assuming you didn't, just copy it from somewhere. And if you come up with subquadratic on the exam, well, just give you a PhD right now, and you could just leave the course and start teaching computer science instead. All right. All right, let's do the next one after that. This is fun. Or at least it's fun for me. I don't know about you guys. So next one says it's almost the same problem. So efficient algorithm, n points in the plane. Now we want the points to be collinear, but also equally spaced. So it's a slight, tiny variation. So equally spaced means the same distance between the first two as the second two. This distance and that distance are the same distance. So they're not just lying on the same line, they lie on the same line in equally spaced intervals. How many worked on this one? Okay, how many have an algorithm for this one? Okay, less people didn't work on it, that's okay. How fast is your algorithm? N squared. N squared log n? Okay, n squared log n you can do. This one you can do n squared without too much difficulty. It's simple enough that we can explain it in class without wasting multiple lectures on it. So we will do that, n squared. So this can be done in n squared pretty straightforwardly. Well, I don't know about completely straightforwardly, but nothing is completely straightforward until you see the answer, then it's straightforward. Right? Reminds me of this joke, this famous mathematician, and supposedly this actually happened once, giving a lecture and he's trying to prove something and he's getting stuck and getting frustrated in front of a class. It's a graduate course, I don't know, in Cambridge or something, and he can't prove it, and he starts and gets stuck, and he starts again, and this happens for a while, and then he tells in frustration, he tells the class, okay, you guys all wait here, I'm gonna go find out the answer. But the way the joke starts, he's putting this theorem on the board. He says the answer is of course obvious, and he's trying to move on to other things. And one meek student from the back of the class says, "Excuse me, professor, I don't see why it's obvious. Could you please, explain it to us?" And he goes, "Sure." And then he gets stuck and he can't do it. He gets flustered. He goes out to his office, and of course he's an illustrious, famous professor. So everybody's just sitting there waiting, and comes back 20 minutes later with a bunch of scribbled notes and goes, "Yes, I was right. It is obvious." Sometimes that's how it is. It's obvious in hindsight, but not when you're trying to solve it. Just like a lot of issues in life are like that. Okay, but I digress. How do you find equally spaced collinear triples? Yeah.
For every pair of points, can be the distance, and then you get the equal distance pairs, and then just see if it's collinear.
So you find pairs of points
With equal distance.
equal distance.
And then, for its collinear, it's going to be constant time. It's going to be a constant time if statement, right? If it is having a single point in a pair, and if
Okay, so he's saying find the segments, connecting pairs, just like we did the previous problem, and then I suppose sort them by. Are you going to sort by?
Yeah, you can sort it, and then you just find the pair of points with the very same distance, and if they are collinear, they're going to have one point in common and the same slope. And that's, I guess, it costs the time.
Yeah. Of course, you're sorting n squared things, right? There's n choose 2 segments. And if you're going to sort n choose 2 segments, already you're spending n squared log n time. So it's not quite quadratic. It's almost. You said n squared log n, right? What was your technique?
So initially just sort the points with respect to any axis, let's say x-axis, and then choose every pair of point, calculate the median and check if the median is present in the points of interest.
Yeah. So for every pair of points, you can look for the third point. And how do you look for the third point? So notice when 2 points are collinear, well, any 2 points are collinear, but if 3 points are collinear, now they're equally spaced. And when they're equally spaced, oh, thank you. I should give you extra credit for pointing that out. Thank you. I hate when that happens. All right, so this distance is the same as that distance. Now, if the points are collinear but not equally spaced, the third point, if you have a pair of points, where can the third point lie if they're just collinear but not necessarily equally spaced? The third point can be where? For a fixed first pair of points. Anywhere on that containing line. That's defined by the first 2 points. But if they're equally spaced, when can that third point be? Where could it be? Either on one side or the other. So if you have a pair of points, the third point can either be here or it could be on the other side. These two and that one are all three are collinear equally spaced. That's it. There's a third choice, a third option in the middle. So the third point can be in the middle, and that's still collinear. These three are collinear right here. Is there a fourth option? Right. The last option was a little less obvious than the first two. But still, is there a fourth option for the third point in red to be equally spaced collinear with the 2 points in black? How many say no fourth option? This is it. This is the 3 cases. How many say there's a fourth possibility, a fifth maybe? How many say this is it? These 3 are it? Okay, only a quarter of the class is voting, so I wonder how obvious this is. Okay, take 10 seconds, think about it. You have 2 points. You want a third point that's got to be equally spaced and collinear with the first 2. So it's got to lie on the line, first of all, to be collinear. It's got to be equally spaced with the first 2. So that limits the options to how many cases? These 3 cases. Is there a fourth place to put the red point that's collinear with the first 2 black points? How many say no? That's correct. There is no other place other than these 3 choices. All right, so having said all that, because they're equally spaced, it highly constrains the location of the third point to only 3 places. In the original problem before, previous problem, it just had to be collinear, so the third point could have lied anywhere on that line. There's a lot of different options, and there's a lot of points floating around in the input. And it's not easy to see which one would be collinear with the first 2. Here, it's much easier. That third point can either be there, or there in the red spots. So for every pair of points, and as n choose 2 of them, you need to see if any of the other points are one of those 3 red choices. And that's your algorithm. How many can see that? That's correct. That will work. What's the time complexity? How fast, given 2 points, can you see if the third point is one of those 3 red choices?
Select different cells. So I can also go ahead and log in if the points are sorted out.
Yeah, so sort the points. So you remember to do a fast search if a point is in a set or not. I give you n points, and then quickly you want to quickly search the set for the first red point, for the second red point, and for the third possible red point to see if any of them are actually members of the original set besides the 2 points that we fixed in black. What do you have to do to the points, and how fast can you search them to be able to determine if a point is in or not in that set? What's the search look like? What can it look like? I'm sure there's lots of ways to do it. All right, let's back up. Let's solve this subroutine separately from this problem. I give you a bunch of points. And then I give you a query point. I ask you, is that query point any one of those other points equal to them or not? I give you a bunch of points and I ask you, is the point 5, 7 one of them? How fast can you do that? You can do it in linear time, right? Obviously, you can compare it to each and every one of the points. But I don't want to necessarily compare each one of the 3 red points to all the black points in the original set. That's too much work. Because back to this subroutine, if I ask you another time and another time, the point set is fixed. There's n points, and that's fixed and not changing. But I have a lot of queries coming at you. For each query, you need to tell me if that query is one of those fixed original n points. So if it's just one query, you can do it in linear time. 2 queries, maybe linear time twice. But if I give you thousands or millions of queries, do you really want to take linear time per each? Could you speed it up using pre-processing, like we've done for many other problems? How do you speed it up? What pre-processing do you have to do? Sort. Now you're getting it. Sort by what? By the x-axis. And if a bunch of points have the same x, sorted by y. Disambiguate by y. Sort by x first, then within x by y. And that's okay, you can do that. How long does it take to do this sort? N log n. And how fast is each query now? Log n. By what technique? Yes, my Padawans, now you're getting it. Any questions about that subroutine? Sort by x, then by y. Then you can do queries quickly by binary search, logarithmic times per query. End of story. Right? Back to this problem. For every pair of points in black, then what do you do?
Confine the search.
For every pair of points in black, try to find this red point in the original point set. And then try to find this red point in the original point set. And then try to find this red point in the original point set. And if one of them is there, you got yourself an equally spaced collinear triple. If not, if none of the 3 red points are in the original point set besides the original 2 black points, then what? Are you done? You got to change the pair to another pair and another pair. Look at all pairs. And for each pair, do this lookup, binary search, kind of lookup in the original point set to see if the first or second or third red candidates are there or not. So what's the total time complexity? N squared log n, yes. But the bottleneck is no longer the sorting. How long does the sorting take? Only n log n, because there's n points. But we're not sorting pairs anymore. We're sorting just the points by their x's and y's as their secondary key. So the bottleneck is doing n squared binary searches now. Question? Yeah, so you're saying you don't necessarily have to look at do all the searches? Yeah, that's a very good insight. He's saying you can avoid doing some searches because if you have this pair and you find this as the red, what you could do is not even look at that middle one. What you can just do is eventually, when you look at these two, you will find this as the alternative point, the third point. Yeah, true. But now, in order to avoid those extra searches, you're going to have to spend some time figuring out which searches are superfluous, and that will take you some time. Maybe even more time than the searches themselves. So you have to kind of balance one against the other. In general, it's hard to avoid doing a quadratic number of searches. Why? Because you can have a point set that no triple is collinear, much less equally spaced. No 3 points lie on any one line. They're all non-collinear. All triples are non-collinear. How do you even determine that? Well, for every pair of points, you're going to have to determine that no other point lies on that line. Never mind is even equally spaced with it. So you may have to look at all pairs, simply because there are no triples that are equally spaced, much less they're collinear, much less equally spaced. So there's no way to avoid any searches. You see what I'm saying? So so in the worst case, you'll have to do a quadratic number of searches. But sometimes you could avoid it. I see. Well, so in some cases you can avoid doing some searches. But let's say all you know is that these 2 points are in a set. These 2 black points are in a set. The red points are not there at all. So unless you do 3 searches right now, no other future pair will induce you to do the right search now that would detect a triple right now that's actually there. Because the red points, none of the red points are there. But you don't know that unless you look. Anyway, so in general, what you're saying is valid. You know, you can avoid some searches in some scenarios. But in general, I think there's worst case scenarios where you cannot avoid doing a quadratic number of searches. You may be able to avoid a few searches, but not below quadratic asymptotically. But that's a very good point you're making. He's trying to optimize it even further, which is good. It's always a good instinct to try to do that. All right. So now we have n squared log n. Algorithm. Let's try to reduce it to n squared. And that one is a little bit tricky. So let's do it the following way. First, we're going to make the observation that if 3 points are collinear, tell you what, before we even do that, right out of Polya's book, General Problem Solving Technique, this problem is two-dimensional, right? Points in a plane. Plane is x and y is 2 dimensions. Because this problem could be 3-dimensional. How many see that this problem is perfectly valid in 3 dimensions? Because there's equally spaced, there's collinear, nothing changes. So you can try to solve this problem in 3 dimensions. Some problems if you can solve them in 2 dimensions, what should you try then as a general problem-solving technique that's also mentioned right in the Polya book that I hope all of you read by now? You can't solve a 2-dimensional problem, what should you do? Try to solve it in 1 dimension, or 1 less dimension than whatever the problem is. If you can't solve a problem in 3 dimensions, try to solve the 2-dimensional analog. If you can't do that, try to solve the 1-dimensional. Because trust me, if you can't do this 2-dimensional problem, you won't be able to try to do the 3-dimensional problem or the 17-dimensional problem. No, it only works in 1 direction. Right? The lower the dimension, the simpler it becomes. Now, some problems trivialize when you reduce the dimension enough. So if you just want to find a collinear triple, what's that problem like in 1 dimension? Yes, all you're asking is, are there any points in the input? And if there are, it's a 1-dimensional problem. They're all on the same line because it's 1-dimensional, right? They just have x's and no y's. So, the collinear triple is trivial in 1 dimension. You just say, are there 3 points? Yes, okay, they must be collinear because they're in 1 dimension. So that's not particularly enlightening here for collinear triple. But collinear equally spaced triple, the 1-dimensional version is not trivial at all. How many can see that? Because, yeah, all the points are on the line, sure, but you're still being asked, are any 3 of them equally spaced from one another? That's not obvious at all. How are you going to solve that in 1 dimension? Well, you tell me, how are you going to solve that in 1 dimension? Let me ask you a leading question. Will the 2-dimensional solution that we saw a few minutes ago work in 1 dimension? How many say yeah? How many say no? The yays have it. Of course it works. Because when we solved the problem in 2 dimensions, we didn't say anything about the values of y or x or how they relate to it. You just said there's a bunch of points in the plane. If all the points happen to be in the plane and also on the same line in the plane, this algorithm still works. It better work. Otherwise, it wouldn't be correct. Right? So in 1 dimension, you can solve it in n² log n, simply by the exact same method that we did before. For every 2 points, look for the 3rd point either on the left, on the right, or in the middle, and you can do that using binary search, and end of story. n² binary searches, a total of n² log n time. 1-dimensional version. Let's try to get the 1-dimensional version to n² from n² log n. And then we'll try to extend it to 2 dimensions. So we're just following Polya's infrastructure of problem solving. Reduce the dimensionality, try to solve it there, and then increase it back up and see what has to change, if anything. All right, how do you solve this in 1 dimension? In n² time. Aside from picking for every pair, doing a binary search on the 3rd point, because that's too expensive. That will get you into n² log n. You're trying to stay within n². So if you have a bunch of points on a line, how can you tell me if any 3 of them are equally spaced? Aside from looking at a pair and looking for the 3rd, either left or right or middle. 2? Yeah, what do you say?
Take the difference
Take the difference.
between the two pairs.
So let's have 3 pointers on the first 3 points. And let's say, let's make them a little bit kind of uneven. We're going to march these pointers around, assuming they don't roll around away from us. So if the first pair of points is closer than the second pair, then what? This is not equally spaced. Everything's collinear, so you don't have to worry about collinearity. But it's not equally spaced. So we move the second pointer here and the third pointer there. And now it may be equally spaced. But let's say it's not even equally spaced. There's a slight difference in the distances. Let's say the distance between the green and the black is smaller than between the black and the blue. The first pointer we're going to leave alone. We're going to leave the blue pointer where it is. And the other 2 pointers will keep doing this. How many see what is going to go on here? Yeah. So depending on what's greater, the distance between the first 2 or the second 2, we're going to move either the second pointer or the third pointer up. And eventually we're going to find any equally spaced triple where the first point is that one, fixed, unchanging, the blue one, and the other 2 can vary. So I'm going to look for all equally spaced triple where the first point is fixed to be the first, but the other 2 can vary. And I'm going to do it by moving these 2 pointers out. And I'm only going to have to scan these 2 pointers out until I reach the end, and that's it. There's no backtracking necessary. How many see that? Yeah. How long does this process take? For the blue one being fixed at the first and nothing else. Linear. How many see linear for these 2 points? Because they're only moving in synchrony. They're not just moving alternatively, because this one can move a bunch, and then this one can only move one later. How many can see that? Depending on the pairwise distances, how they compare. So notice, all right, so once I march these 2 pointers out, what do I do next? Make the blue one the second guy, reset these 2, and keep going like this. And then make this blue one the third guy, reset these 2, and then keep going like this. What's the total time? N squared. And if there's equally spaced triple, this will find it after n passes h1 linear time to a total of n squared time. Notice what we've done here. We didn't do a binary search. We folded all the searches together. We batched them up so that they only take constant time each. We just didn't do the searches in the order like we did before, but we did all of them. We batched them up. How many see this conceptual abstraction? We merge all the searches together into a bunch of scans, linear scans. But that covers all the searches. You no longer have to do a binary search. Because it wasn't just one binary search that we did. We did n squared binary searches before. If you just do one binary search, there's no way to avoid it. If you want to do n binary searches or n squared binary searches, there's a way to buy it wholesale, not retail, right? To amortize the cost and avoid doing a lot of individual searches, and instead of batching them up, and per search it'll become cheaper. So per search, you're only spending constant time. It's one abstract way to think about it. Okay. So now we've solved the one-dimensional version, and it wasn't completely trivial. Obviously, it wasn't trivial at all. This pointer marching, doing n scans, avoiding the binary search. Do we still have to sort? I mean, say we still have to sort something. Yeah. Why? Yeah, because sort by the x. Because the points don't have to come in order. They come in any random order they choose. So you sort by x, and then you can do this pointer marching. End of these scans. Yes.
But should it be also fix the second and third exception, and then increase the second one?
No, because the pointers can permute. They're commutative, right? So as long as you fix the first at every single point, anchor it at a fixed point, and then the other two can march, you can, that covers all possibilities, if you think about it. See, another way to think about this, with the binary search method of the previous method, we looked at a pair and looked for the third. Here, we're doing something different. We look at a single point and look for the pair. How many can see the difference? So we look, so we say, what other 2 points can belong with this blue one? And then we look for the pair, as opposed to fix a pair and then look for the third guy. We fix a single point and look for the missing pair. And this will cover all pairs that can coexist with this first one in an equally spaced manner. Okay. How many understand the one-dimensional version? All right. Now extend it back to 2 dimensions. It shouldn't be a huge leap of an imagination now. Yeah.
You just look at the x values for the points. The x values would have to be equidistant.
Yeah. So he's making the astute observation that if a triple of points is equally spaced in 3D, their projection to the x-axis, in other words, just their x-coordinates, never mind the y's, what is true about the x-coordinates of this triple of points in 1 dimension, their projection to the x-axis? If they're equally spaced and collinear in 3D, in 2D, the projections in 2D are what? In 1D, also equally spaced. How many can see that? Yeah. So project all the points to the x-axis, in other words, ignore the y's, solve the problem in 1D, and then you'll see if it's equally spaced triple, with one possible caveat, one possible exception. Yeah, the projection could be equally spaced, but the points themselves may not be equally spaced. So sure, 3 points like this can project into equally spaced one-dimensional projection, but so can these 3 points. These 3 green points also have the same projection as these 3 black points because they're the same vertical lines. So it's not an if and only if. If the triple is equally spaced, the projection is equally spaced. But if the projection is equally spaced, the 3 points may not be equally spaced. It's not an if and only if. It only works in one direction. How many can see that? Yeah. So what's your algorithm now?
So you need to check the y projection
Yes.
in the same order.
Exactly. So the simple way to describe it is check. When you find an equally spaced one-dimensional projection, go back to 2D and check that it's truly equally spaced in 2 dimensions also. So if you find this equally spaced projection, check to see that the 3 points that they came from are like this in black, not like this in blue. And that's easy to do in constant time. And there's your 2-dimensional algorithm. Will this work in 3 dimensions? How many say yes? Yeah, pretty much. Just project 3-dimensional points to the x-axis, dude. Make sure it's equally spaced in 3D. Will it work in 17 dimensions? How many say yes? Yeah, it will. Nothing stops it. What will be the time complexity in 17 dimensions? Say it proud, say it loud. N squared. Right? time the dimensionality, yes. But we assume usually that's a constant. The dimension is fixed to be a constant. Yeah. So it'll be n squared times d the dimension. Very good observation. What if all 3 points are collinear, but the line is parallel to the y-axis? It's very good boundary case. What do you say to that? There's several ways to handle it. One of the ways is when you first start with a point set, slightly rotate it by a fixed angle so that doesn't happen. That's kind of a clean general way of doing it, is avoid pathological cases where they're all parallel to the x or parallel to the y. Another way of doing it is so there's nothing magical about the x-axis. If you used the line y is equal to x, diagonal line, this will still work. Just project it to any line you want, not just the x-axis. How many can see you could project it to any line and this will still work? Yeah, of course. So find a line that doesn't have that pathology, project it with respect to that line. That's not too hard to do. I'll leave the details up to you. But that's a very good point. Let me make it one final point. This method found a collinear triple if it exists. What if there's 2 collinear triples, 7 collinear triples, 50 collinear triples? Will this method find all of them, or just some of them, or just one of them? How many collinear triples will it find, this method, in 1D, or even in 2D, because they're almost the same algorithm? How many see all of them? Yes. So it finds all collinear triples, not just one. And it takes linear time to find all collinear triples. So that solves another problem for free, because here we look for all collinear triples. Actually, this problem asks for a little more, not just triples, but maximal collinear subsets. But the point is, we found all collinear triples, not just one. And how many collinear triples can there be, maximum? Worst case pathological case. In 2D. Or even in 1D, but let's say 2D. How many triples do you think it could be, worst case? Take a wild guess. A constant, linear, n log n. You know what? For extra credit, let me know what the answer is next time. The maximum number of collinear triples you can have in the worst case. Because this reports all of them. So obviously it's not going to be more than quadratic. Prove to me it's not more than quadratic. That proof is easy, right? For every pair, the third one being collinear, equally spaced, could be at one point or another point or another point. There's only 3 candidates for every pair. There's only n choose 2 pairs. It's a quadratic maximum. Show me a lower bound that's as close to quadratic as you can on the low side for a worst case example. Extra credit for next time. All right, anything else on this? So, none of the problems we talked today will be in the midterm, but others will. All right, see you next time.
Why is n squared n log n time searches, not n cubed log n?
For the original, for the previous problem. So you're doing n squared searches because there's n choose 2 pairs. N choose 2 is n squared.
For the determining if there's if any 3 points are collinear, for that one, I think I missed.
You could do n cubed triple pairings and then check each one for collinearity. But it's not necessary because you can sort everything by slope and y-intercept. And when you do, the y-intercept and the slope pairs, the y-intercept and the slope pairs will be next to each other in the sorted list. So if there's one pair that falls on the same line as another pair, because the right,
One long string.
then all four of them fall on a line. Two of them could be the same point, but not all three will be the same, because then there'll be three different. They'll be the same pair. So if two different pairs fall on the same line, there's either 3 points on the line or 4 points on the line. And by a scan, you'll find out which. So you just have to sort n-squared objects, all lines containing pairs of points, not triples.
But the sorting would be n log n. Right?
It will be k log k, where k is n squared.
So it's n squared log n squared,
Yes.
which is
Lo-
2 n squared log n, which is n squared log n.
Exactly. There you go. The beautiful properties of asymptotics.
So just a little bit question. So when we are talking about finding the collinear points in a higher dimension, so what we are essentially doing, like you said, like 17 dimension case. So we are essentially projecting it on 1D or 16D.
1D.
1D. So what happens if we project it on 1D and all the points have a projection of a point? Then you have to check all the 16 dimension pairs. I mean, every pair.
So what we said earlier, you find a projection line
Okay.
where there's no collisions.
There is no collisions. So, but it would be hard to find. I mean,
No, because you have n squared time to find it. Because the whole thing will take n squared time. So before you start, find a line where no two x's collide. I mean, it's not trivial, but it's not going to take anywhere near n squared time.
okay, because you have to check, like, I suppose in every dimension. But let's say between axes, so you can have 180-degree rotation.
Let me give you a quick solution to this. Let's say all the x and y coordinates are integers. Make the projection line slope pi and y-intercept also pi.
Okay. Okay, so nothing with the idea. Or you can make it E also.
Yeah, make it something irrational.
Yeah.
But all the points are integers, so they're not going to project. You see what I'm saying? So you can quickly find a line that is in no danger of creating a pathological case.
Okay, but you need to find a line that is a single dimension for it to project.
Technically, you don't even need to do that because the line is an abstraction. You can basically treat the points based on their projections on some hypothetical line that doesn't have this pathology. Doesn't mean you actually have to have a line and compute the line.
Yeah. Yeah.
You can sort of pretend that you do and still end up with the same
So
result.
I mean, yeah. So
It's just a way of comparing things.
yeah. So means the distance part that essentially you are comparing between the two objects.
Yes,
Yeah.
Yeah.
Yeah. I mean,
the distance on the projection, and so you can think about it even more abstractly than just a verbatim projection onto a line. But another way to think about it is use the x-axis, but first rigidly rotate the set by an epsilon angle, and make that angle, you know, 1 over,
yeah. A normal means
1 over pi, or make it something irrational angle.
normal origin shifting.
Yeah. And then, because this problem is invariant with respect to rotation.
Yeah. Yeah.
So rotate it by some irrational angle, and then you'll have no pathologies.
Yeah, I get it.
So there's lots of ways to think about it.
Okay. Yeah.
But
Thank you.
it's a good question. Yeah.
Thank you.
Hi, Professor. I'm still a little confused why when you fix the first pointer and then it takes only linear time for the last 2 pointers to find the
Yeah. So if the first pointer is fixed here, then the other two are highly constrained where they can be. Because if this pointer is already to here, there's no point in moving this forward. It's not going to be collinear.
Oh, yeah.
You need to move this one forward until the distances are equal. But if it reaches a point where this is larger than this, there's no point in moving this up. This needs to move up. So you're going to move it like this.
Okay, gotcha. Oh, basically, you need to check the distance between those
Yes.
two pointers and
yes,
that two
compare it to that.
pointers.
And if this is larger, this one better move. If this is larger, the middle one needs to move
Okay, gotcha.
to make it equal.
I actually have another idea to solve this problem because when you have like a two pair of point and you can there's only three different possible for the third one. So why we just use a hash table because it's very easy to calculate the 3 points.
Because it's not constant time hash table.
Um,
And you're going to be doing n squared accesses of the hash table.
oh yes, yes.
So it'll
that's
be
correct.
n squared times the hash table worst case, which is at least logarithmic and possibly linear unless you're doing height balanced trees off the buckets. Nice try, but hash table is not constant time. It's constant time on average, not worst case.
Okay, gotcha. Thank you so much.
This will be average time n squared, your algorithm.
Okay.
But worst case will be worse than quadratic.
Oh, so this is for the optimal. It's asked for the it didn't ask for whether it's like an average, the average time complexity or the optimal.
Usually we mean worst case. When you talk about time complexity, it's worst case behavior, the worst it can be. So like sorting, if it's already sorted, bubble sort works in linear time. Because it's already sorted, so nothing gets changed and you can stop right away. But that's not the worst case. So bubble sort is not linear time because the worst case is still quadratic. So you have to always think about the worst case. Unless you ask about the average case or some other, but that the assumption is the worst case, unless otherwise specified.
If it's not specifically asked for the average case, it's just assuming we need to consider the worst
The
case.
worst case, yeah.
Okay.
You certainly don't want to consider the best case. Because that's almost meaningless.
Okay.
If the list is already sorted, there's no work to be done. But you haven't even. But that's not a general solution.
Gotcha. Thank you so much.
All right, sure.
I'm sorry, I guess इसको point करना है क्योंकि ये change हो गया अब तेरा नया ये बन गया ना और change होने के बाद तेरा इसका right क्या है